Hello everyone, welcome to our talk. This will cover some of our recent vulnerability research we've been doing on DisplayPort. My name's Simon and this is Ross. So today what our aim is to try and cover the process that we followed when we were building our platform-independent DisplayPort Fuzzer. This fuzzer was quite successful, found quite a number of bugs, so hopefully it'll be interesting. So we're going to kick off with a little introduction of who we are. Then we'll go through some technical background of what DisplayPort is, how the protocol works and what it's used for. And then we'll go into details of how we built the fuzzer, how it works, and what it can do. We'll then try and do a live demo before covering a few details of some of the bugs we found, and then hopefully have some time for some questions. So we are the cyber research group at Raytheon UK. We're a fairly small team, and we do fairly niche security services. We provide these to the MOD as well as other government departments and some internal Raytheon teams. We've been doing cyber research at Raytheon for about 7 or 8 years now. However, in 2019, we formed a new team under our strategic research group. And in this, we focus on a few areas such as vulnerability research, product characterization, and digital forensics. Most of our researchers work on a mixture of customer projects as well as their own research, and this is funded by Raytheon. And this talk is an example of that. So all this DisplayPort research was funded by Raytheon, and it's no connection to any of our customers. And if you find this interesting and you want to work with us or work for us, we're currently hiring, so please visit our website or drop us an email.
Hi, good afternoon. So I'm just going to introduce some fuzzing terms, just briefly. So a simple fuzzer sends some random data, known as a test case, to a program to see if it crashes, basically. It's typically more effective to randomly mutate some valid data or an input corpus. And this is the approach that we will be using as we can apply this kind of testing to many types of devices. And we'll loop through this sort of flow diagram many thousands of times during the fuzzing campaign. And in this presentation, we're going to describe how we achieved each step. So why DisplayPort? It's a popular interface. It's quite ubiquitous. Now it's supported over USB-C. It contains a bidirectional auxiliary channel, which the DisplayPort uses to negotiate video transmission with the display. And critically, these messages on this channel are processed by the graphics driver, which is typically operated at a privileged level. So there's some potential for some interesting bugs. So there's a lot of research in HDMI. It's not a great amount there's no research that we found on DisplayPort. Public research. So as well as providing some research on DisplayPort, our presentation will go a bit more in depth on how to create the hardware required to target many of these types of devices. I guess the other takeaway from this slide is these sort of bugs have been around for about a decade. So I guess lessons learned hasn't really happened. So what is DisplayPort? It's a digital display interface. It connects a computer or a source to a display or a sink. So I head over to Wikipedia. It tells me that it carries video, audio, and data over channels. And then there's a reference to other data and points to the DisplayPort specification, which we'll have a look at next. And the specification states that there are 3 main channels. There's a main link, which is the high-speed video link, which carries video in one direction only from the computer to the display. There's a hot plug detect, which is basically a pin, which when driven high or voltage is applied, it'll wake up the computer. And there's the auxiliary channel, which is a bidirectional communication channel. And this is what we're going to target. So what is the auxiliary channel for? Well, this sequence diagram contains some of the messages found on the auxiliary channel when you connect to a display. Hot plug detect triggers a software interrupt. The graphics driver will make a read request, and the display will respond with some data which is passed by the graphics driver. And this data includes EDID, or display capability information, such as resolutions, etc. And when setup is complete, video transmission starts. There are many more protocols which are supported by DP, the DisplayPort, EDID, which I mentioned, but there's others which support encryption, topology, discovery, encryption, I said, and some other messaging systems. And some of these are quite complex. So our aim is to create a platform-independent DisplayPort Fuzzer. And we want to target many devices. And this means we need to know how to transmit and receive messages on the auxiliary channel. So we have to understand the DisplayPort specification from the physical layer up. At the physical layer, we need to understand the characteristics of a differential signal, or LVDS. At the top, we've got a typical signal from a microcontroller. And at the bottom, we have a differential signal, which is used to carry the auxiliary channel messages. And basically, voltage polarity is used to represent bits on the line rather than voltage amplitude. And differential signal is used as it supports high data rates, and it copes well with noise. So we need some electronics to convert between the single and differential signals, and this is called a line driver, and it's represented in this image by the triangles. So serial signals from your computer will be converted to differential signals as found on the actual cable itself, and then that's converted back again on the display side. The other thing to note on this slide is that the transmit and receive electronics share the same channel, and this is called a half duplex, as only one side can transmit at a time, which is why the auxiliary channel is a request-response-based messaging system. So you can observe the differential signal by connecting an oscilloscope to the 2 pins on the DisplayPort connector. The bottom image is the 2 traces from the top overlaid. You can clearly see the characteristical differential signal here. We can also see data. So how is the data encoded? Data is encoded using Manchester encoding, which basically means data is XORed with a clock signal. And this is useful because it requires less pins on the connector. It breaks up long periods of high or low. And this suits the electrical characteristics of the channel. But it also means that we can distinguish between other markers and data, which I'll talk about next. At the link layer, we need to understand how the data is framed. So this helps the receiver identify when the message is on the channel. So the channel is idle to begin with, and then it's at the start of the message is identified with zeros, and then there are 2 markers. So you got the first marker and the second marker, and these identify the start and the end of the data. So as mentioned earlier, these markers don't conform to Manchester encoding, therefore the data section can be clearly identified. And these sections help when implementing a state machine, for example. And just to note that the data can be further divided into other things depending on what protocol is used. That's done in software. So the auxiliary channel is a request response based messaging system, and they are framed in exactly the same way. And this makes it easy for us to change our fuzzer to mock a sync or source device. So, for example, we can target multiple types of device, such as a display or a computer. And as you can see, there's a short period of time in between the request and response. There's a maximum of 300 microseconds, but typically we want to be much shorter than that to keep timings down. And this is a constraint that we need to deal with when designing our system. So messages are handled at the application layer. Messages like EDID, as I mentioned earlier. And this simple example shows the display capabilities such as resolution are encoded in the data. Messages are typically processed in the graphics driver. And so using the electronics described earlier, we can promiscuously observe messages on this channel between a computer and a display. And these messages provide us with an input corpus for the fuzzer, which leads to how we develop the fuzzer. I'll hand you back to Simon.
So what was our goal? So our initial goal was to develop a fuzzer for a GPU driver. So on the screen, you can see there's a diagram, and the GPU is the source device on the left, and our fuzzer is pretending to be a sync device on the right. And we've got some data we've captured off a bus from connecting a monitor to a GPU. We've intercepted that captured valid data. What we do is we mutate that data. We then send a hot plug detect. We send that high, so the GPU sends a request. And essentially what we're trying to do is send a mutated response, so a response which is invalid, and then we detect to see whether the target's crashed. So what might this mutated response look like? So the GPU might request 4 bytes, and instead we might return a single byte, but we might set the size field to 99 bytes, and we'll sort of see what happens, really. So what stages did we go through? So at the very beginning, we read the spec, or certainly little bits of it. It's incredibly long, hundreds and hundreds of pages, and also it's quite hard to get hold of the spec. Technically, you have to pay, but you can find it if you Google. Then once we got that and we understood, how we can interface with this specification, this protocol, we started building a hardware interface so we could read and write data on this channel. Once we could do that, we then started building software to decode the protocol, as well as be able to record the data we see on there. And then once we do that, we've got something that we can get rid of a monitor, we can plug our fuzzer directly into a GPU, and we can mimic a monitor. So we can just replay data that we've previously captured. Then we add in things like mutating of test cases. So we start adding a bit more randomness, and then build the fuzzer up, adding crash detection, recording test cases. And then if we get lucky and have some crashes, we can then add functionality to replay those crashes and minimize them, turn them into sort of proof of concepts. So as Ross said, we've got a differential signal, but it's much easier for us if we turn that into a single-ended signal, because we can then use a microprocessor quite easily interfacing with that. So one of the first things we did was we trawled through RS, Farnell, looking for something that would meet those needs. So we got an LVDS interface chip that essentially we needed something that supported 3 volts, could do at least 1 megabits per second, as the auxiliary channel can cope with that. So we had to cope with that speed, and we also wanted something that could both send and receive data, so it had to be a driver and a receiver. As well as all that, we had to sort of comply with the DisplayPort spec. So there was a useful diagram in the spec, which you can see at the bottom right. You can possibly see it anyway. And this was very useful, so it tells us exactly what components we need to essentially interface with the bus. So we have to use some pull-down resistors, we have to do termination resistors, and also some AC coupling capacitors there. And this allows us to essentially be a monitor and drive that bus, and the GPU will be able to detect that. So this is sort of the circuit we came up with to start. You can see all the discrete components there are connected to the DisplayPort channel, and that goes into our LVDS chip. And then we've connected the output of the LVDS chip into a logic analyzer, essentially. So on the bottom, you can sort of see, essentially, you can see the sync frames, then you can see the end of sync flag, some data, and end of data marker. And on the right, it's just a little picture showing sort of our initial prototype, pretty nasty. Essentially, we took a knife to a DisplayPort cable. But it works, and it's quick. So now we've got this signal. How do we digitalize it? We need to get it into something so we can process it. So essentially, we had two options that we could come up with. One was use a microprocessor, one was use an FPGA. We went down the microprocessor route because it's just much quicker to develop. People have told us use FPGAs, but it would have taken ages. So in the end, we settled on a Tinsy 4.1 board. It's got an ARM processor on it that runs at 600 meg. It's got USB on there, so we can get data in and out pretty quickly. As well as that, it's got some good hardware peripherals there. So it's got DMA, timers, and lots of useful things like that. So we've got a microprocessor that runs at 600 meg, but what we actually found was when we first implemented it, we triggered it off interrupts and did all the processing in software. This could read fine, but when we started trying to send data as well, it just couldn't keep up, and we were losing data. So we had to get a bit creative, and in the end, we settled on a design which offloaded a lot of this onto the hardware peripherals of the Tinsy board, so we could actually chain a lot of the hardware peripherals up. So we chained interrupt controller, timer, and DMA engine. So the interrupt controller was configured to generate an interrupt every time the signal went high or low. This was then went into a timer. So the timer was essentially measuring how many clock cycles the signal was high or how many was low, and feeding this into the DMA engine, which put it into a circular buffer for us. So we end up with a circular buffer with lots of data in there. And essentially then all we need to do is write a optimized C code state machine, which could quickly go around that buffer looking for the sync patterns. And when it sees the sync patterns, it knows in between those sync patterns we've got valid data. So it can then decode that using Manchester encoding, extract all the commands, address, and data, and chuck it out the USB port. And then this also works in reverse. So if we want to send data, we can receive data on the USB port and do the opposite. So what do we interface this with? Essentially, we wrote some Python code on a PC, and this was sort of the master of the fuzzer, so it orchestrated everything. It's communicated with the hardware interface board, as well as generating us test cases. So we recorded test cases from a normal interaction over the wire, and then we used an open source library called Romanza, and this would mutate, so it would add randomness, flip bits, things like that. And we could then take these test cases and we could feed them into our hardware interface board, which would put them on the DisplayPort channel. This fuzzer would also handle things like logging the test cases to disk, which wouldn't have been very practical on an embedded device, as well as doing crash detection. So we did crash detection in the end via ICMP. So a target like a Windows PC. Essentially, you can keep pinging it, and then when it crashes, it will stop responding to pings, so you know you've had a crash or something's gone wrong somewhere. So we made several different modes that we could support. So the first thing we implemented was a sniffer mode. So essentially, this was the hardware interface board, and the fuzzer would sit between a monitor and a GPU, and we just capture data. So we'd build up a library of what sort of valid data we'd see across there, and this would then be used in our fuzzing runs. We then moved into adding functionality to Fuzzer source device, so Fuzzer driver, GPU driver, by using that test data and mutating it. And then we had then added a feature to sync Fuzzer, a sync device, so a monitor or a display. We started off by using just completely random data. So we didn't respect the protocol at all. So if we were asked for 4 bytes, we might return 16 bytes or something like that. But what we found was certain GPU drivers didn't really like that. So they would detect as soon as you sent too much data, they'd just throw everything away. So you wouldn't get very far into the driver or find any interesting bugs. So we added a new mode, which we sort of termed a goodish mode, which would respect the basic protocol. So if we were asked for 4 bytes, we'd return 4 bytes, and we'd do things like ACKs properly. But the data inside that protocol was mutated and essentially invalid. And what we found was if we started fuzzing in normal mode for a day or two, and we hadn't found anything, we'd switch then into goodish mode and leave that for a week or two. And that sort of was quite effective, that approach. So what did the architecture look like? So in the top left, we've got our PC running some Python code. And then in the top right, we've got the GPU in a desktop PC. The fuzzer's doing crash detection by pinging it, but it's also controlling the power to the PC. So what we found was in certain cases, the PC would crash so badly that it wouldn't reboot, it wouldn't be responsive at all. So essentially, we had to add something to automate power cycling it. This Python fuzzer would then talk via USB to our hardware interface board on our Tinsy board, which would then interface directly into the DisplayPort cable, so it can inject data in and receive data via our LVDS transceiver and discrete components. So what did the hardware look like? We started off with a fairly rapid prototype, I suppose. Lots of cables and sort of loose connections, which worked pretty well. This lasted a few months before essentially we found it was a little bit unreliable when you're working from home and you've got toddlers and cats. They like to pull out cables, which isn't ideal when you're fuzzing for a couple of weeks. So we then moved to developing a proper PCB, which looks better and it's a bit more reliable. And essentially on that, we've got 2 ports for connecting either a GPU or a monitor, and some jumpers there to configure what you're fuzzing. So what does a basic fuzzing run look like? So this is when we're fuzzing a GPU. We start up in the top, and our Python code at the top is generating some test cases for us from the ones that we've recorded. We then will send a number of these to our hardware interface boards. The Tinsy would buffer up maybe 500 samples. The Tinsy would then toggle the hot plug pin, which would kick the GPU off. So the GPU would then go, oh, I've got a monitor attached. It'd send a request, and we would receive that request in the Tinsy, decode it, and then we'd select an appropriate test case to respond with, send this to the GPU, and then the GPU, we'd go around this loop multiple times, essentially, until either the target crashed or we ran out of test cases. So this bottom loop on the left would just keep going round and round there, millions and millions of times. Right, let's try a demo. So I've got my Python code on this machine, and then we've got our hardware interface board connected via USB to this laptop. So essentially, this is just a command that's just telling our fuzzer to replay some test cases. So we've got some test cases that we've built as a proof of concept, and we're going to send this to our Tinsy board, which is on COM8. And then the Tinsy board is receiving it, and it's now going to start replaying test cases. So GPU will be sending requests, and we'll be responding with hopefully bad data. And with any luck, it'll crash. Hey. Cool. So we've got a crash. What do we do now? So we've got blue screen of defs. The first thing we did was see if we could reproduce it. So essentially, when our fuzzer detects a PC crashed, it logs all the test cases we've got. So this might be, 1 million test cases we sent it to crash. So it logs that, and it would replay them. And if it crashed again, then it goes, great, I've got something that's, nice and reliable and reproducible. The next step would be to collect a crash dump. So PCs like Windows, Mac, when you get a crash like that, they'll write a log file to the disk, and you can configure them to write a small one, large one, whatever. So we'd pull that off, load it up in a debugger, and we could see exactly where it was crashing, what function was causing it, what driver it was, and essentially from that we could see whether we found another unique crash or whether it's just one we've seen before. We then take our, say, 1 million test cases, and we try and minimize that. So essentially we keep removing test cases and replaying it over and over again until we've got right down to the minimum amount of data we could send to cause a crash. So we might get this down to, from sending 1 million requests and responses down to like 20 or something like that. Once we've got these smaller test cases, we then look to decode them into human-readable actions. So in the top right, you can see an example of the data. It's not a 0 day, don't worry. So you've got 80006. And essentially, we wrote a Python script which scanned and parsed the DisplayPort specification, so it scrapes data from all the registers. And it could then take in data like that and decode it into human-readable form. So we can see that maps to a request message that's doing a DisplayPort native write to a address hex 600, and it's is writing 1 byte, which is 01. We're then responding with an ACK, but we're just adding some Fs for fun, so we're sending 6 bytes back as well. And this goes on and on. Essentially, once you've got a few test cases there and things like this, decode in human readable form, you can then analyze them, look for patterns, and then develop a proof of concept. And then the next stage is essentially you can disclose it to vendors, and with any luck, they fix the bugs. Now hand back to Ross to talk about some of the bugs.
Yeah, so the Fuzzer is a success. Through a lot of hard work, we've got some bugs. I guess more importantly, the vendors are releasing some driver updates. But unfortunately, we can't go into any details as we're still going through coordinated vulnerability disclosure. But we can talk about the types of bugs that we found. It's worth noting that no privileges are required for this type of attack. As you've seen, the demo PC screen was locked. The crashes were triaged, as Simon mentioned. We discovered a number of issues, as you can see, some of them more interesting, like out-of-band writes. And we also target some sync devices, such as a display, and found issues there. Sort of highlights that software issues are present in many types of devices. And just to reiterate that the physical access is required. Mitigation is quite difficult, as we've just violated our first rule. So just to summarize quickly then, we identified a high-risk target which had no public research. Researched how DisplayPort works. We used this to prototype some hardware to read and write auxiliary channel messages, and then use that to create a platform-independent fuzzer, which discovered lots of bugs, and started some coordinated vulnerability disclosure. But there's more research that we can do. There's areas where we can optimize the fuzzer. We could test more devices, triage more issues, and of course continue to work with the vendors to fix these issues. Thank you very much. Any questions? Yeah, any questions? Stunned silence. Yep. Are we going to open source it? Unfortunately, we can't because we're still going through vulnerability disclosure. Obviously, we've got this material, but we can't disclose that just yet. Yeah, so we monitored the target if it crashed using ping. It's a simple case. Yeah.
Basically, just got to look at it. Yeah.
Oh, sorry, for a monitor. Yeah.
How long did it take, sort of, the initial idea to exploit the first part?
So from sort of coming up with the idea, I suppose, until developing and finding the first crash took quite a while because we weren't working on it full time. It was sort of just in between projects. It was kind of a lockdown project, I suppose. So it's been on and off, I suppose, for a while. Probably a couple of months, I'd say, to find the first bug. And then it was just, I mean, it was quite quick and easy to get a device to crash. The difficult bit was then turning that into something that's reproducible and consistent, and sort of detecting that the target crashed and capturing the test cases. That took quite a bit more work. But getting just a PC to crash was quite easy, really.
I know you can't tell us much about vulnerabilities, but can you give us an idea of the quantity of vulnerabilities you found?
Probably not. Just to say, there's quite a lot, more than we expected. I don't really know. I think most of them looked like they were in the drivers, but sometimes we were seeing weird things with GPUs as well. So sometimes GPUs would just hang and the fans and then would just go crazy. So we'd have no idea what's going on there. But down to the vendors to try and work out. Cool, I think that's it.